Okay, so having completed the proof of Fibonacci theorem, let's now go back to the original idea of this section, that is sums of this type. F of x, where x varies over x, where f is a real valued function on x, that is x with x as its domain, and x is a countable set. And we have seen that such a sum makes sense only when it is absolutely convergent, which by definition is this. A sum like this is called absolutely convergent if there exists a bijection G. Well, this is not R, but this is X. A bijection G between the set of natural numbers and the set X such that this infinite series is absolutely convergent. And when that happens, we say that this infinite sum sums to, that is, has the value this itself, that is its own sum. But this is the definition of absolute convergence, and in case you have absolute convergence, the definition of the value of this kind of sums. But can we have another characterization of this absolute convergence? And yes, we have, and that is the next result. So this is lemma 8 to 3. So let X be a countable set and let f be a real valued function on x, that is, let f like this be a function. Then the series we can call this kind of sums series also, because after all they are series. Then the series is absolutely convergent if and only if. Now we have the condition, the equivalent condition for absolute convergence, which I will write on that side. If and only if a supremum of the supremum of a set of a particular set is finite, and A is finite, this supremum is finite. Okay, so let us now try to see what this lemma is saying. This lemma tells us about this set, and in fact its supremum. So what do we see in this set? What are the elements in this set? The elements in this set are finite sums of what? Of the f values, or actually the absolute values of the f values, over what? Over finite subsets of our countable set X. So if we collect all the finite subsets of X and over them we calculate sums like this, then we are going to get a set of sums. This is that set. If its supremum, that is its least upper bound, is itself finite, then our original series will be absolutely convergent. And conversely, if this is absolutely convergent, according to our definition of absolute convergence, then this supremum will be finite. One thing, of course, you can immediately see is that since the elements in this set, that is these sums, just from the look of them you can see that all these sums are going to be non-negative real numbers. So their supremum is also going to be a non-negative real number. So the supremum being finite or not being finite just depends on it being less than plus infinity or being equal to plus infinity. Okay, so that's the thing. So we do not write anything on this side, because we already know that whatever this quantity ultimately turns out to be, this supremum, it is always greater than or equal to 0 due to the nature of the elements in this set. And its proof is the first exercise actually. So we are going to prove it when we solve the exercises. So this is C. Exercise 8-1. So when we start solving the exercises, then we will start proving these things also. Okay, now note that this criterion, it's a criterion for absolute convergence because it is a necessary and sufficient condition for absolute convergence, and which does not mention any such bijection G or anything. Instead, it characterizes absolute convergence in terms of finite subsets of the given set. Now, based on this thing, there is a possibility of extending the definition of this kind of sums from countable sets X to arbitrary sets X, which may be uncountable also. And that is the thing we are going to see in the next definition. And we say an extension of this kind of sums because here our X is countable, because we only know such sums, or we have so far only known such sums when the underlying set is countable. We do not know what the meaning of this kind of sums will be if the underlying set is uncountable. But now this lemma has given us a possibility of doing that, and that we are going to do using this itself, this condition. So that is the next definition. So let's see the definition. Although we have so far not seen any concrete example of an uncountable set, we are saying we are going to extend this kind of sums to possibly uncountable sets X, but we so far have no example of an uncountable set, but we will soon see. In the very next section, we are going to see examples of uncountable sets. The set of real numbers is, for example, one uncountable set. So this is definition 8 to 4. Let X be a set. Now X is just any set. So in brackets we write not necessarily countable. Okay. X may very well be an uncountable set. And let the rest of the setup is same. We are going to have a real valued function with X as domain, and then we are going to consider such a sum. And f from X to R be a function, then we say that the series is absolutely convergent if such a thing is true. That is the exact same thing A is a subset of X and A is finite if this supremum is less than plus infinity, or in other words, if this supremum is a real number, then we say that this series is absolutely convergent. Note the difference between these two things. Our previous infinite sum, where this X was countable, already had a meaning in terms of the original definition of absolute convergence, that is, which depends on the existence of a bijection G from N to X and all that thing. But this is another thing which also has the same meaning. In fact, that's what the previous lemma says. I mean the lemma that comes before the definition, this one, that says that series being absolutely convergent according to the original definition of absolute convergence is the same as this condition. But now we are again defining absolute convergence for a sum like this, like the previous sum, but now our X may not be countable. So in particular, when X is not countable, then this sum already does not have a meaning. We are giving it a meaning, and that meaning has been given in terms of this condition itself. So now we say that this series is absolutely convergent if this thing happens. And you know that in a definition, if means if and only if. So this being absolutely convergent means this is true, and if this is true, then that means this is absolutely convergent. Okay. right? But here the situation is still a little bit, I won't say problematic, but it's not, we are not going to directly get a sum for this series now in this situation where X is a general set. Like how you got the sum of this series when X was a countable set to be the sum of this series. Right. Here, however, we are just simply saying that if this condition is true, then this is said to be absolutely convergent, but we are not immediately able to say what the sum will be or what the meaning of the sum will be. But before that, we go to that thing, before we go to that stage, we need another result which will enable us to define the sum of this kind of series where X may be an uncountable set, and that is the next result. So in fact, before the next result, this is what the author says. The author says this: note that we have not yet said what the series this is equal to, or what its sum is, or what its value is. This shall be accomplished by the following lemma. So this is another result, which is a fact about absolute convergence of this kind of series. So this will be 8 to 5. Let X be a set. Again, we remind ourselves that this may possibly be uncountable. Let X be a set and let f from X into R be a function such that the series is absolutely convergent. It is given that this series is absolutely convergent by the previous definition, of course. Then the set of all elements X in X such that f of X is not equal to 0. The set of those elements where f does not vanish is at most countable. That means either it's countable or it is finite. Then the set is at most countable, and this gives us a chance of defining the value of this sum when it is absolutely convergent. So this is how okay, I need to, but before that I need to say about the proof. This also is one exercise this is the second exercise. So then the author writes, because of this, we can define the value of the series or the sum of the series when it is absolutely convergent by the following formula. Okay, so that means we are considering only those x for which f of x is not equal to 0. This makes sense because we are replacing the arbitrary set x in this sum with the set this which we know is at most countable, and that at most countability of this set comes from the previous level. Keep in mind this is only a definition. Okay, the value or the sum of this series has been assigned to be, has been defined to be equal to this. But it makes sense, and this definition is natural also, because normally when you think of this kind of sum, right, then the zero values are not going to contribute anything to the sum. If you just vaguely think about it without being too rigorous, you just intuitively think about the series, the zero values in a series do not contribute anything to the sum. So that's why it feels like the right choice that we should consider only the non-zero values, and luckily when you consider the non-zero values, the resulting set turns out to be at most countable. So here either you are looking at a series over a countable set which is covered by the original definition, that is the first definition of absolute convergence, or you are looking at a series over a finite set, which also we have seen previously when we discussed that kind of sums, that is sums over finite set. So it makes sense. But there is still one more thing that needs to be mentioned about this extension of that we have seen today. Okay, so now here is the thing. Say X is a countable set. Right? Then you have this series where f of course is a real valued function on X. Now you have two different definitions of absolute convergence of this sum. One of them says that this sum is absolutely convergent if there exists a bijection G such that this series is absolutely convergent. That is our original definition. This is absolutely convergent. And the other definition that we have seen today says this, that this sum is absolutely convergent if the supremum of this set A is a finite subset of X. The supremum of this set is finite. Now, of course, the link is that lemma which tells us that if this sum is absolutely convergent according to our old definition, and which applies in this situation because X is a countable set, then this happens. But is it really enough to say that the two definitions are consistent? That is, when this is absolutely convergent with respect to the old definition, then it is also absolutely convergent with respect to the new definition, and conversely. It may seem like this is true, but we are going to discuss more about the consistency of these two definitions when we start solving the exercises. Okay, we are going to come back to this thing. So the author just simply mentions one part. Note also that this definition, that means the new one, is consistent with the definitions we have already had or we already have for series on countable sets, precisely this issue. So we are going to come back to it and see in more detail what this entire consistency is about. But right now we move on. So today we are not proving anything, in fact. We are just simply stating the things, the results, the definitions, and we try to see what they say. So the proofs we will do afterwards. Now here comes the next result, which gives the general properties of this kind of sums over arbitrary sets. This is proposition 826, and it has a name also. Absolutely convergent series laws. or in other words, loss for absolutely convergent series over arbitrary sets. So again, let's start like this. Let X be any set not necessarily countable. Let f be a real valued function, and we are going to have to consider another one. G is also a real valued function. Both have X as their domain. B functions such that the series this and this are absolutely convergent. Both of them are absolutely convergent according to the new definition. Then we have these facts. The series summation fx plus gfx as x varies over x is also absolutely convergent, and its sum. Now we have a meaning of the sum. You know what that is. It involves the non-zero values of the function that is there in the series. So according to that meaning, the sum is just this sum plus this sum. So you see that in this very general situation also, those series laws continue to have the same form, okay, which is what we expect when we extend a definition. We do not expect everything to happen similar to what we previously had, but the more similarly we have things, the more it is our belief that the definition or the extension, the new definition, has been natural, whatever this word natural may mean. But of course, when we keep on extending things, at some point things are going to deviate from what we normally see. And in fact, if that does not happen at all, then things will become very boring and monotonous. That's not the case here, however. And in part B we have that real if C is a real number, and if you multiply each term of this series by C, then that one also is absolutely convergent. That is C times f of x is absolutely convergent, and its sum is just like before, C times the previous sum, C times the sum of the original series. So that is part B. Then part C, if the original set X can be split into two sets, if X is the union of X1 and X2 split into two subsets for two, not just two any subsets but two disjoint sets X1 and X2, then the series of f of x, but now x varies over x1, and the other one which involves x2 are both absolutely convergent, and the original series sum is equal to the sum of these two sums. And there is a converse to this also. Part C is not over yet. Conversely, if H is a function from x into R, now we are considering another function, okay? But for this function, conversely, if H is a function from x to R, is a function such that these two series are absolutely convergent, then the sum of h of x as x varies over the entire set x is also absolutely convergent. and you still have the same thing. And then there is one more subdivision, one more part D. If y is, well, in the text the author writes another set, I mean besides x, but this another really does not mean that y is different from our original x. It may be x also. If y is another set and say g from y into x is a bijection, then this series f of g of y as y varies over y. Oh, we can, okay. We cannot take g, no? Because we already had one g in the beginning of the statement. So let us call this k, say. Then this is a bijection. Then this series is also, just like the original series f of x, absolutely convergent and its sum is equal to the sum of the original series. No change at all. So that's the statement of this absolutely convergent series laws, or these are the laws, and its proof is also one of the exercises which we will see later. See, it is, in fact, it's the third one. Okay, so here I would like to end our discussion for tonight, but before I leave let me say briefly what we are going to see next. I mean, apart from the proofs of these things, we have already seen that things can go wrong. I mean, I am talking about an ordinary series of real numbers, right? Things can go wrong if a series is not absolutely convergent, right? You go back to the definition of absolute convergence of an ordinary series of real numbers. In fact, let's just recall that. Say you have this ordinary series of real numbers where each an is a real number. We say that such a series is absolutely convergent when this series is convergent. This series is just convergent, ordinary convergence. When that happens, we say that this series is absolutely convergent. And we have already seen that when this happens, when we have absolute convergence, then we can rearrange the terms of this series in any manner whatsoever and get the same sum. Okay, neither is the convergence affected nor is the sum affected. But when a series is not absolutely convergent but conditionally convergent nonetheless, so then we say that the series is conditionally convergent but not absolutely convergent, then the situation is very bad if you try to rearrange things. We have already seen such things, and one example is this series. It's a convergent series, but if for this series you consider it is convergent by the alternating series test, by that test, but if you consider this series for this, then you get the classic harmonic series, which you know is divergent. So that means this series is conditionally convergent but not absolutely convergent. And when we rearrange the terms of this, not this series of course, rearrange the terms of the original series, then all wild things happen. How wild can it get? It is extremely wild, as wild as you can get. The thing is that if you have a series like this, which is conditionally convergent but not absolutely convergent, then you can rearrange the terms to make the series converge to any real number. You can also rearrange the terms to make it diverge to plus infinity and also to minus infinity. In fact, this ability of such a series to be to have such drastic behavior when we deal with rearrangements is itself a result by Riemann. So that is the last thing in this section that we are eventually going to see. After we complete the proofs of all those things, we are going to see Riemann's theorem. There we are going to prove that that can be done. That is, given a conditionally convergent series which is not absolutely convergent and any real number R, you can create a rearrangement of the terms so that the rearranged series converges to R. It is that bad. Okay, so that we are going to, it's somewhat very striking, this result, but it is a truth. So we will see these things. So let me just end things here itself, and the next upload is this coming Tuesday, where we are again going back to group theory from Herstein, where we are, I think, right now we are solving problems on permutation groups. So we'll keep on doing that. So that's just it. So see you on Tuesday with Herstein's problems. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.